about a library I've been working on for a little bit. So I'm Spencer, by the way. I'm from the MIT Media Lab, and my Twitter and GitHub are both SSFRR. So I've been doing Julia stuff. I first learned about it. Angel Pizarro, this guy in the Philly tech guy, gave a talk at the functional programming meetup about Julia like 2 years ago. And then about a year ago.
Where was that?
Philly, like the Philly Lambda.
So yet another example of an MIT guy that learns about Julia somewhere else.
Yeah. Well, I wasn't MIT, so.
Yeah. You're at Harvard.
That was pre. No, I am now. I wasn't.
Right.
This was like 2 years ago. So I've been doing Julia for a little bit. So my background is in signal processing and like music information retrieval. Trying to pull information from unstructured audio data and do kind of machine learning type stuff on top of it. So I was doing some of that with some audio data, and realized that there was no way for me to like get my processed audio and listen to what it was, aside from just like writing out a WAV file to disk and opening it up, and then listening to it in some other sound editor, which I thought was kind of an annoying workflow. So I figured, okay, well, like I should, somebody should be able to implement some real-time audio stuff in Julia. So I figured I would go ahead and give it a shot. Before I talk about AudioIO in particular, I want to go a little bit into the background of that sort of informs some of the architecture of it, and then I'm going to go into some of the design decisions that went into it. So this is a modular synthesizer. This actually belongs to my PI. He built it. And I think this is, so basically like the way that a modular synthesizer works is you have all these different modules. Like each one, like this little box here is a module that might be like an oscillator or a filter, or there's some sequencers in there somewhere. There's like a bunch of different modules that kind of take inputs, spit out outputs. They do different things with them. They have control voltages, so you can like affect parameters. You can turn knobs. You can plug them in different ways. And so all these different wires are basically how you perform on this instrument, is by rewiring up all of these modules in different ways to make different sounds. And so that kind of paradigm has been around for a long time. People have been using these. They kind of went out of fashion for a while everyone got excited about computers. They're kind of back in style now. People are getting into analog. But anyways, so that concept of modular synthesizer is something good to kind of keep in mind. This is Max Matthews, the guy on the right, who's kind of a computer music pioneer. So he wrote one of the first, I think basically the first sort of computerized digital music system called Music. And it later informed some other programs such as Music 2 and Music 3. So those were like very highly successful. And then they decided to change, some names started changing. There's now C Sound, which is also heavily informed by that, which is actually still in pretty wide use today. There's a bunch of other ones. There's Max MSP, there's Pure Data. Those are both very similar to each other. They're kind of graphical languages. There's Chuck, which is pretty cool. Also kind of a text-based language. SuperCollider and Overtone. Those are interesting because Overtone is actually using the same audio backend as SuperCollider, but it's basically a new front-end enclosure, so you can do all of the control in more kind of functional style. So this is Max MSP. This is a patch that I built earlier this year for this installation for a sensor data thing we were doing. And so you can kind of see how you use this you have all these different objects that might take audio in or control signals in. They have various outputs, and basically you can wire them all up to each other in different ways to make different sounds. So that's sort of this very visual paradigm, and these are great for a lot of things. They don't typically do iterative sort of things are kind of tough to express sometimes. If you have something that you want to like spawn a bunch of massive things in parallel, a lot of times you end up like copying and pasting a bunch of little boxes next to each other. So there's a lot of things that are kind of tough to do. So I kind of have been looking for a way to move more back into kind of leveraging the skills that I've developed as a programmer, and using those in a to do my music stuff. So another kind of example of people using computers to do music stuff. This is actually a duo called MetaX, and if you look in the background, you can see some computer code. And so what they're doing is something called live coding, which is kind of getting bigger. I mean, obviously it's not like mainstream, but there's more and more people who are basically performing using programming in front of an audience where they can, the audience can kind of see what's going on. And so they're doing a combination of they have some controllers down here that have buttons that they can push, but they're also writing code real time and evaluating it, and that causes things to happen in the audio synthesis. And their nice quote from their website: "Their sound isn't hardcore, breakcore, or speedcore. It's multi-core and fully hyper-threaded." Had to add that. So there's this concept of UGens, which is also called unit generators, and that's something that sort of is common across a lot of these different music systems, where these unit generators are, pretty much analogous to those modules in the modular synthesizer. There are all these little pieces that you can sort of hook up together. So like this is another example. This is actually like a screenshot from Pure Data blown up real big, where you might have a noise generator, you have an oscillator that just makes a sinusoid. And then you can, I want to multiply by a constant, I want to add a constant to it. This is a filter, and so you've got some noise going into your filter, and then you're modulating the frequency of the filter, through this input, and then you're spitting it out to the output. So you're kind of taking all these modules, you're plugging them all together, and then you've got that, sound that's flowing around. So you have, this environment, whether it's, a text environment or a graphical environment, where you can sort of wire up all these modules together, and you can build sophisticated logic by how you route these things together, and so the question kind of arises then is, okay, so like where do these modules come from, right? Like, do you have a limited number of these modules? Can you write your own? How does that work? And so for the most part, yeah, you can write your own of these modules. But sort of to do that, like if you wanted to write a new C sound UGen, you do it in C or C++. If you want to do a new Maximus P or PV UGen, it's C or C++. Super Collider, only C++. I guess you could write it, the C++ would do it, but their whole API is in C++. Closure, they also C++ for the actual UGens, for whether you're using Overtone or Super Collider. So this is the very familiar two-language problem that we've had that in scientific computing has Julia is looking to address. So what I'm hoping for is that for Julia we can do have it be Julia all the way down. This is the Basset. So AudioIO is a library basically to be able to build these things and wire them up together, but also build the really low level objects, all kind of in the same environment all the way through. So I want to talk a little bit about the kind of what functions we export. I have one AF open. I think I'm probably going to change this to just AudioIO.open. So I don't want it to. So like overall, I'm looking for what are the concepts that are expressed. So like play is a concept that most other libraries don't use. So I'm not too worried about like overlapping it. And also we can apply that to to the types. So I'm trying to, for the most part, use the multiple dispatch and not have like a bunch of these underscore names. So AF open is probably going to be, because I want to be able to open a string and have it automatically know that it's an audio file and do all the parsing there. So that's where it overlaps. So I can't just do. I can't just have like the object instantiation stuff. So this is the type signature for a for instantiating basically. Right? So first we're just instantiating an array of floats, right? And then if you want to play that array, you can just do play array. So part of like one of the driving forces about for the library is to try to keep things really, really simple for the simple things that you would want to do. And so I don't want to have to worry about like opening. So there's a lot of stuff that kind of has to happen behind the hood to be able to play something out of your sound card. But the idea is most of that should basically pick reasonable defaults and go for it. So you can just play a 432 and that works great. But you also might have int16, right? So you might have a different, or int64. You might have different formats for your array that you want to be able to play. And so for the most part, what I do is I kind of make some assumptions about common ways to format audio in audio samples. And so if it's natively AudioIO uses Float32 for all of the processing. So in the vectorization, the fact that Float32s tend to vectorize better, I was pretty happy about that because I'm going to start using that. So internally we all use float 32s, but you can give it an int16, and basically it'll right now just assume it's a fully, your full range, and it'll scale it down. So this is basically what the function signature, if you want to do play, if you give it an array of signed integers, basically it just divides it by the max to scale it down to -1, and then it calls the play. So then you get a new array of float 32s, and then we're going to play that array instead. So then, audio buff is an array of float 32s, so that throughout I didn't have to keep typing array of float 32 all the time. So if you already have something that's sort of in the native format of the system, then it doesn't need to convert it. It can handle it directly. And so that's something that I do a lot throughout the library, is that there's sort of some sort of like a native thing that it's expecting, and I handle how to do it there. And then if you give it something else that it doesn't handle natively, I basically have wrapper functions that convert it to the thing that it expects natively, and then handles it. So I have like tons. I have a lot of short functions that sort of do this kind of conversion. It makes it really easy to add new ones. So this is where it starts to do something a little interesting, and we're not just passing down the play function. We're actually instantiating this array player thing. And so this is where we sort of start to get into that same UGen idea, where an array player is going to be sort of this node. You can think about this UGen in this render chain, which is something that knows that knows how to spit out audio. And then I'm going to play that UGen. So here again, so we are kind of continuing to divert that into play, where if you take a unit generator and you call play on it, it's just going to send that unit generator to the sound card, kind of whatever it is. So here again, we're deferring, and then also I'm doing some splatting to be able to pass along these arguments. So what happens when you play a UGen? This is where things get a little interesting. So oftentimes you'd want to be able to play to a different stream. Like you might you might know a little more about which audio stream on your computer you want to play to. You might want to stream to like an IceCast or something so people can subscribe to the web on the web. And so you can call play. You can give it a stream argument, and it'll play through that stream. But if you don't give it a stream, the idea is we're just going to basically have this kind of global, default stream that it's going to instantiate if you don't give it, and then it'll start playing through that. So this is basically the one kind of global thing that I'm doing to handle the sort of default stream thing. So then what happens when you actually want to play something through a stream? We're going to keep diving down into play. So basically every stream has a root node, which is basically kind of a mixer. And all that we're doing is we're adding it to that, and then we're returning, right? And so at this point, it pops back up the stack, and that execution is over. So you're like, okay, well, where does the actual playing happen? Like, how did that happen? So back here, when we started this stream, what the stream does, it spawns a task, and that task is sitting there in the background and basically rendering rendering frames of audio. It connects to port audio. I'm using port audio for all the audio backend, and port audio actually calls a callback once every 6 to 200 milliseconds, like however big your buffer size is, it'll call a callback that often. And it expects you, as in your handling of that callback, to be able to fill up an audio buffer. You hand it back, and then it'll take care of spitting that audio out of your sound card. So I'll get in a little bit later on how some of that presents a little bit of a challenge. One thing that I'm not going to talk about in too much detail is just like the multi-threading stuff. It gets called in totally separate context. So I've got a little C shim that subscribes to that, that registers the callback and then communicates with the Julia task via a semaphore and a file, like a file descriptor, and that's how basically like that the kind of ping pongs back and forth between the two different contexts, while still the Julia code is all running from within the Julia thread. So that part was a little tricky. I do need to take that shim and put it into pure Julia code. So basically all that we do when we want to play something is we just add it to that render tree, and then that other task that's sitting there and rendering stuff is going to, it's just going to start. It's going to start playing. It's going to start calling on that for that function. So what kind of audio nodes do we really have here, right? So for instance, you might want to play a sine oscillator, so at 440 hertz. So you just want to go. That's probably out of chance. But that's about what you get. You can do white noise, so that's just like it's just noise. This one's awesome. And so this is what an audio. So all those things are instances of audio nodes. And the audio node is basically the UGen. I might just change the name to UGen because that's I think probably more common nomenclature. And so it's sort of like the basic, the basic thing that you can wire together in this system. Now this isn't the first iteration of what audio nodes look like, and this is this was sort of has been an interesting design process to figure out how these, how to represent these. So initially what I had was I basically just had audio node as an abstract type. And then all of the various other types of audio nodes, oscillators and white noise, and I don't have any filters yet. But so those guys are just were concrete subtypes of this abstract audio node. And so I thought, okay, cool. So like if you can use typing system, everything's happy. But the problem is that then I started wanting to add behavior to wanted to add behavior to all the audio nodes together, and especially because of the way that I have things happening in these different tasks. There was some state involved with that kind of had to get passed around, and so right now specifically the active and actually I can highlight that. So active and end condition are common to all of the different audio nodes, and so originally I just had active and I just added it to all of my audio nodes, and then I had to add this end condition, and I'm like, oh crap, like this is a pain. Do we have to add it to go through it and have to add it? And I kind of was thinking that let's say somebody else in their in some other library that uses AudioIO, they want to make their own UGens, and so they, I don't want them to have to add new fields every time I want to add a new field to the base case. So what I ended, so then there's the renderer is the is basically how I handle that now in that all of the specialized functionality in terms of the difference between playing a sinusoid versus playing a bunch of white noise. The difference happens inside of this renderer type, and you can see in the main one, not that guy. So T here is a subtype of audio renderer, and so all the specialized functionality basically can kind of get pushed into that, and I can use parametric typing basically instead of needing to put field basically this was my answer to why I don't need fields in the abstract type in abstract types. And there's actually a second option also that kind of alleviates the need for fields in abstract types that I think is actually also pretty equally good, and it's they're pretty subtle differences that are almost mostly aesthetic. I also think it's a pretty good option to just sort of package up any of your common state into a single type, and then have all of your subtypes basically have one field that's that type, and then you still get the ability to add extra fields to that later on without any of the other objects needing to know about it. I think those are both good options to how to deal with that. I was talking to these guys quite a bit about this, and I was like, oh man, I really want fields on abstract types. Really solve this problem, it'd be great. And kind of after going through this design process, my thought on it now is basically that there are plenty of ways to make things needlessly complex given the tools that we already have, and that I feel like we don't need anymore. Anything that you want to do, between parameter types, you can do all kinds of craziness. So so basically, the renderer is where all of that the specialization sort of happens, and then There's some things also in order to make, so from the client side, when a user wants to create a new sine oscillator, I don't want them to instantiate an audio node, curly brace sine oscillator renderer. That's not a great API for them. And so basically, the base case is you can create an audio node with a renderer, and basically this just gives me some default values on the two, and basically just instantiates it with this kind of a standard constructor. But then you can also if you just create an audio node, then it will, and this will be a little more clear later on when I show the constructors for the individuals. But basically, I'm just going to instantiate an audio node, and I'm going to give it the I'm going to just pass along all the args to the interior renderer guy. So that makes declaring the other guys a little bit easier, and I'll cover that in a bit. So this is like an example of one of these renderers where so this one basically takes a set of inputs and it mixes them together, right? So these are all the inputs that it might, it can have kind of an arbitrary number of these audio node inputs. It stores a buffer so that it doesn't have to reallocate that every render cycle. It can kind of reuse some of that same data. And then this is how you instantiate just the renderer, right? So again, I'm kind of doing this thing where if you give it the data, it's gonna create just as you kind of the way you normally would expect it to, and then I'm kind of creating default values. I could make inputs equals audio node. I kind of like making it more explicit and having a separate constructor for it. That's just style thing or whatever. So then this is where this is where it gets a little bit magic, and so this is the part that I kind of I feel a little bit more iffy about, but I've come to terms with it. And where basically I'm going to create the ability for clients to basically they can just instantiate an audio mixer. So like a user of it just creates an audio mixer, and kind of behind the scenes I'm creating this audio node of the mix renderer, and then whatever arguments that they give to it basically just end up getting passed into the renderer itself, kind of as it goes through the audio node constructor. Originally, I also had like a bunch of default value handling stuff here, but the kind of arg splatting that I added recently to the base audio node constructor, that splatting made it so that I could basically just pass things through to the renderer directly and handle all of those default values and all that stuff at the inside of the renderer constructors. So basically, this is kind of the only extra magic that you sort of need to add if you want to add your own type of audio node. This is kind of what you've got to do. So then the render function. This is really, every one of these audio renderers has to be able to render something. That's their whole reason for being, right? So that's how that is. So creating an oscillator with a constant frequency, that's really cool. But creating one with an oscillating frequency is cooler. And so you can basically pass audio nodes as arguments to other audio nodes. And through the magic of multiple dispatch, you can handle, you can sort of handle that in your, in the parametric types, you can handle it when you're instantiating it. And then the actual render functions, depending on whether, what type of renderer it is, you can have different implementations that are going to implement that. Either just, multiplying the input by a constant value or whatever, but so you can kind of handle that the different behaviors that you want, pretty relatively easily. So some of the things that have been challenging about this, I think especially the latency stuff is a big problem, and just like dealing with allocation. I mean, I spent a bunch of time, I have tight loops, and I was using pi, like the constant pi, and the end result was a float 32, and so doing those conversions was allocating like 16 bytes inside of this tight loop, and so because I'm running that tight loop, 44,000 times a second, it ends up being I ended up creating a lot of garbage, and then the garbage collector would come and kick in, and then my render cycle wouldn't happen within when it had to happen, and so you get these big dropouts. It's a pain. So that's something that I'm still struggling with. I definitely you're going to hear dropouts. It's definitely not solved yet. The new garbage collector code, I run off that branch sometimes, and it definitely helps. I still need to be really, really careful in the code to just really ferret out any unnecessary allocations. So hopefully I can demo this. I did have some issues just now, so I'm going to let's see. Oh, is it showing up that side? So I'm just starting up a Julia REPL in the bottom of my Vim here. Pull up AudioIO. Can you guys kind of see the top relatively well? No. Okay. I can probably. Better? Okay, so first, I guess let's just do 220. So you saw that I just did play sine oscillator. It instantiated the port audio stream and then started playing this through the port audio stream. So you're now hearing a beautiful sine oscillator at 220 hertz. I can stop it too. So that's cool. What about something? So here, basically what I'm doing is I'm playing. I'm creating a function, which is every time I call it, going to play a sine oscillator. So it starts with one that has 30 hertz, but then I'm multiplying that by 100 to basically give it a wider swing, and then offsetting it. So basically, this is this is controlling the frequency, and it'll be centered around 100 hertz. Or sorry, it'll be centered around the note, and it'll be varying by 100 hertz. And then I'm multiplying that whole thing by this linear ramp, which basically over 0.3 seconds is going to go from the value 1 to the value 0. And so the multiply operator is I guess it's not overloaded, right? Multiply is I have a method defined for the operators for audio node, and also so like different combinations of audio nodes and constants will sort of do the right thing. It'll kind of wrap it up in a new renderer that knows how to multiply, and you kind of create this tree. And then I'm going to add a little bit of white noise at the beginning, which is basically like a shorter, a short little ramp of white noise at the beginning. So you can see what that. So now if I do box of, so this is the same. And actually, so yeah, so like getting rid of the console output definitely helps the performance quite a bit. Also, the first time you call any of these things, it JIT compiles, which totally borks the rendering. So I need to also fix the, I need to start pre-compiling things ahead of time so that you don't have that problem whenever you call some new code. So you can also do cool things like mapping. So like this is creating. I'm going to create a list of just for a bunch of these different frequencies. I'm going to call this function, and I'm going to create a list of these audio nodes, right? And then I'm just going to map the play function to all this. We can read and write from audio files. So this is a well-known kind of drum loop called the Amen breakbeat, and it sounds like this. So that's cool. What if I want to play it backwards? So then, okay, so I'm going to take, and the whole thing is cool, but I want to be able to do things with little pieces of it, right? So the first thing I want to do is I'm going to pad it out so that it's a multiple of 32 samples, and then I'm basically going to create a matrix where the columns are each, audio samples, and then so you have as many columns as slices. So I'm going to basically cut it up into 32 slices. So now beats is basically 32 slices of that audio. I could play like beats, all of them for. So that's just one section of it. But here, so basically, this is just a little sequencer object that I've put together that basically, when you play it, it is going to spawn a thread or spawn a coroutine that is going to basically play you can basically give it a sequence of values and then a sequence of durations, and it'll basically like call whatever function you give it kind of sequentially, and it'll just loop calling with each of those values and then wait for each of those durations. And let's make ourselves able to stop it. So we can take that slice, and so here I'm calling this play slice function, or I'm giving it the play slice function. I'm just giving it array, like indices from 1 to 16, so I'm going to basically play the first half of that audio, sort of chunk by chunk, and they're going to be separated by 0.2 seconds each time. So
I don't think
You forgot the play slice.
Yeah, from stop you didn't copy until
You need to evaluate more, a couple more lines.
Yeah.
well, I think I skipped a couple of them intentionally. I think I just need this one. Am I right? Or am I going to look down? Ah, shit. Oh, play slice is not fun. Yeah, no, I see. You are totally right. Now. So it's like a little bit faster, but basically sounds kind of similar to what it sounded like before, right?
Height check right there.
So now what I want to do, so let's do if we change the durations there. So let's play it faster. Faster is better. Slower actually sounds pretty good. And then, so I created that this function that takes one argument that plays stuff. So let's see, this is probably so here. I'm down there. And so there's a whole bunch of stuff that has to happen, I think, to get this guy to make it better. These are some other kind of cool applications that I'm going to skip over for time. So there's a lot more nodes we need to make this better. The latency right now, in order to get kind of acceptable performance, is pretty long. It's like on the order of a couple hundred milliseconds at least. And so if you wanted to use it for real-time audio processing, kind of like as an effects pedal sort of a deal, you really need like 6 to 15 millisecond latencies to make that work. And the new garbage collector, if it's really like hard stopped at 5 milliseconds, I think we might be able to get quite a bit of audio processing done in there and still hit those deadlines. We need to figure out, I need to go through and keep cleaning. Like I've taken a bunch of allocation out, but there's still a lot of places that it needs to come. So like anything that helps to identify places that allocate, any of those tools are super useful. And right now it's pretty, like a lot of things are kind of, you can't create multi-channel streams. And installation's a bit of a pain right now because I have this one little C shim that you have to be able to compile, so you have to have a C compiler on your machine to be able to install it. I mean, it should compile that automatically. It's got bin deps and a build script and stuff, so that should more or less work. But it also on a Mac, you have to install port audio and live sound files separately from Homebrew. So once those get in Homebrew.jl, then I can pull them in easily. So there's still definitely a lot of things you can install story. I think a music theory library would be really useful for like notes and intervals and chords, all that stuff. I think I had a couple things that I whipped together in that little demo of like ways to map on pitches to audio nodes. I think there's definitely a lot of really rich abstractions you can build around that. Error handling's not great right now. If it crashes, you get feedback between the input and the output. And there's a bunch of like utility functions that I kind of have to get mapped out. So yeah, that's AudioIO.
that's like super cool?
Well, I mean, so for me, the biggest thing is the two-language problem.
Yeah.
That in all these other systems to do, music processing and and live performance and all that, like all those systems, you have this whole group of users who use it, and then you have this like separate little team of of people who write all these nodes that people use, and so you have like a much smaller population of people who can write these audio nodes just because of that barrier. And even if you can if you feel comfortable writing in C, you have to like figure out this kind of complicated API. I mean, this is all those issues. It's the exact same set of issues with scientific computing, And so I think that having a system, having a language, having an environment where the same group of people can kind of go all the way down, I think is really cool. Like I think it like that separation between being able to wire things up and then write the actual little things themselves, I think is unnecessary. And so this I think could be a cool environment for that. I mean, I'm still not like it's definitely an experiment right now. Like I don't know whether we'll be able to get like almost nobody is doing this kind of real-time audio processing stuff in any kind of a garbage collected language. So, I mean, like pretty much people write that stuff in C and C++ because of that determinism. So I don't know yet whether it's going to work. Okay.
Well, you very charitably phrased it as you needing to reduce allocation, but in reality, I need to reduce allocation.
I think, but both need to happen. Yeah. Yes.
Does it work without the libport audio library?
No, port audio is how it talks to the sound card.
So it doesn't install with Homebrew right now?
No, so you can install it, like if you have your system Homebrew, you can do brew install port audio, and it'll work fine.
Okay.
The only issue is that it doesn't automatically pull it in when you try to install AudioIO.
Okay.
And once it's, because there's homebrew.jl, which has like pre-built binaries and a bunch of stuff.
Yeah.
And so that's kind of what Bindeps plugs into more easily, and so it's not in there yet. I have issues, I was not good enough to do pull requests, but I have issues. So,
Are you pushing or pulling the samples through the node graph?
I'm pulling. So basically the port audio thread calls the callback and then basically notifies my Julia task, and the Julia task then calls the render function on the root node, and basically that starts this render chain down where the root node, calls the render chains of all of its children, and each one of those calls the render function. So basically, like it's kind of pulling in that data every sample, and then it gets the audio input in that callback also. So the audio input actually gets passed down as an argument down the render chain. And there's an audio input node, which basically all that it does is returns the input and starts returning it back as an output. So that kind of becomes a leaf node of the tree, which is how audio input starts working its way back up. Yes.
Is the multiple dispatch an advantage? You seem to be using it.
I love multiple dispatch.
Yeah.
Oh man, do I love multiple dispatch. Yeah, I mean, it's a really natural way for me to think about just like how to organize these, this structure, and like the ability to have all my play functions, right? Like I guess that's for the most part single dispatch. Like I'm not like doing a lot of different combinations of things, but just like that having all these functions, and then if I want to support some new type of thing that I can play, it makes it really easy to just like figure out where I need to wire it in and do that. I mean, all of the operators, I just have like an operators.jl, which has like a bunch of different implementations of multiply for different combinations of audio nodes and scalar inputs, and kind of create the right type of thing for that. I mean, it makes it really easy to add that sort of handling. I think it makes me a little lazy about not making sometimes like nicer. I probably could generalize some of this a little more so that I wouldn't need to add some of those things like for everything that I want to add. But I don't know. So far, that's been a good thing. It's been really easy to prototype and really easy to kind of like change things.
I should remember, I was told that we actually have to be out of here with all of our stuff out of here by 5 p.m.
Okay.
And so now I guess we should, Dan will lead a graphic session, so maybe we should cut off the question.
Yeah, come talk to me afterwards.
Okay, that's the next.